Hi there, guys. One more time, another video. This time our discussion of quadratic functions will mostly be concerned with graphing. All right? And again, we're going to look at the three different forms of quadratic functions that we have and what those three different forms tell us about the graph. The three different forms all give us different clues about the graph. And the most important parts of the graph, for our purposes anyway, are the vertex, the y-intercept, and the x-intercepts, if they exist. And these are the points that really just help us get an actual image of the graph. For different practical purposes, other points along the curve may be more important for different applications of a quadratic function. But in terms of just getting a graph, getting a visual picture of a quadratic function, those points there, the vertex, the y-intercept, and the x-intercepts, if they exist, are the most important points. So, if you look at an equation written in standard form, really about the only thing that it just hands you that's given in the equation is the y-intercept. That constant in the equation, that is the y-intercept, because when x equals 0, these two terms basically equal 0, and so y equals c when x equals 0. And that's what defines the y-intercept, is where x equals 0. Another thing that you can get with relatively little amount of work is the line of symmetry. All right, this little formula right here, the opposite of b over 2a, gives you the line of symmetry. X equals that number is the equation of the vertical line through the vertex of the parabola. The line through the vertex, the vertical line through the vertex, divides the parabola into symmetrical parts. So therefore, that number is also the x-coordinate of the vertex. Okay? So the opposite of b divided by 2 times a gives us that information. That's fairly easy to come up with. That's about it as far as, either given or fairly easy to find. You can find the y-coordinate of the vertex taking this x value and plugging it back in, but then we're getting into kind of a lot of work, but you can certainly do that. The factored form of a quadratic is really nice for graphing because it gives you the two x-intercepts if they are real numbers. And it wouldn't be in factored form unless they were real numbers, to tell you the truth, quite frankly. This is a little bit oversimplified here, this information right here. It may if there's a number multiplying x in either one of these factors, then it's not just m or n, it may be m divided by that number or something like that. But, in factored form as is, where there's no number multiplying x inside the factor, it's just m and n. Also, the y-intercept is pretty easy to find because, once again, if x equals 0, already I've got 0 minus m and 0 minus n, so negative m times negative n is positive mn, and if there's an a value in there, that gets multiplied in there as well. So the y-intercept isn't too bad to find in factored form, as well as the x-intercepts. Okay, vertex form is super nice though. Its special form gives us the vertex right there out of, in the equation. So that is the only one that really gives you the vertex, just hands it to you. You can get the x-intercept without too much work by letting y equal 0, putting a 0 in there for y and solving it. You can get the y-intercept by letting x equal 0 and just working that out. All right, so both of those aren't too bad to find in vertex form as well. So you might say vertex form really, with what it just gives you outright and what it provides with a minimal amount of work, is probably about the most efficient way we have to graph a quadratic function. Okay, but you'll see all these forms as you go through your math experiences. Notice that in all of these forms, what is common to all of them is the parameter a, and it does the same thing in all of them. Okay, it has the same function in all three forms. It controls the steepness or rate of change, as well as the orientation. All right. So if a is a number greater than 1, then the graph is steeper than normal, all right? Or we sometimes say that it has been vertically stretched. It's skinnier. It's been like stretched upwards or stretched downwards, all right? That's when a is greater than 1. If a is a number between 0 and 1, that means that it is less steep. It is widened out, All right, it's a more gradually increasing rate of change, you could say. Sometimes visually we use the word it has been vertically compressed. All right, it seems to have been kind of squashed down. All right, and then if a is a number less than 0, that means the graph is upside down. We say that it is now negatively oriented. Okay, positively oriented when a is greater than 0 means the parabola opens upwards, and negative oriented means that it opens downwards. Okay, so that's the information that the three forms of a quadratic function give you in terms of the graph. Now I'd like to say something in reference to an earlier video that we made, and that is that when you solve a quadratic equation, those solutions are called the roots of the equation. No matter how you come by those roots, whether you're solving it from the quadratic formula or by factoring or by completing the square, the solutions are called the roots, and if those roots are real numbers, then they are also the x-intercepts of the graph. And I wanted to show you something about that in relation to the special vertex form, which I do particularly like. But when you solve the vertex form, set equal to 0, in other words, replacing y with 0 to find the x-intercepts, let's take a look at what happens here, because it's kind of interesting. When you just take this general case here, solving it for x, okay, so I move k over. I got negative k now on the right-hand side. I divide both sides by a, so now I have this, negative k over a equals x minus h squared. When I take the square root of both sides, including the plus minus, I've got x minus h equals positive or negative square root of the opposite of k over a. All right? So that little fraction right there is kind of interesting. When I finally solve it for x, x equals this h value plus or minus this square root of k over a, negative k over a. If this gives us real numbers, in other words, I've got an actual positive quantity here underneath the radical, notice that opposite of k doesn't necessarily mean a negative number. If k was a negative number to begin with, then moving it over here would be positive, and that would be the opposite of k. So, or if a is a negative number, then I'd be dividing by a negative number, and that would also give me a positive quantity underneath the square root. So even though this looks like I'm taking the square root of a negative number, keep in mind k could be positive or negative, and so could a. So if this does give me a positive value underneath the square root, these are real numbers, and check out what happens here. Remember that in vertex form, h is the x-coordinate of the vertex, all right, and k is the y-coordinate. So here's a parabola, vertex hk. The line of symmetry is x equals h, right? And so on the x-axis, there's h, directly above the vertex of the parabola. The x-intercepts are equidistant away from this point. And how far are they? Well, they're this far. This plus or minus the square root of negative k over a, if I add that to h, I get this x-intercept, and if I subtract it, I get the other x-intercept. All right? So that's kind of an interesting relationship between the solutions to perfect square form, even when they were irrational, perhaps, and the x-intercepts. They are directly related to the vertex. They are equidistant away from the vertex. If you apply that, interestingly, to the quadratic formula, you kind of get the same thing. It's a little bit more complicated looking as far as the algebra goes. So let's say we've got a standard form equation. I solve it with the quadratic formula, and I have this negative b over 2a plus or minus, and I notice that I'm splitting up the fraction for the normal representation of the quadratic formula. Usually we write it as one fraction with one denominator, but I could write it as two fractions with the same denominator. And this negative, the reason I'm doing that is because, as we've learned earlier, that the line of symmetry for a parabola is this negative b over 2a. Just like it was h, in the vertex form. In standard form, we're using different numbers now to come up with the same value, which is negative b over 2a. Here's the vertex. All right, there's the vertex, and there's the line of symmetry for the parabola. I've still got this same, plus or minus some quantity here. If if I take a little bit of a simplification, let's say b squared minus 4ac equals some letter d, for example, like standing for discriminant, maybe? Anyway, I've got this fraction right here, this thing, is the square root of a number over 2a. Okay? And it's plus that number and it's minus that number. Here's our line of symmetry, negative b over 2a, plus this value and then minus this value. It's exactly the same thing that we were showing up here, okay, with that line of symmetry where it crosses the x-axis, plus a number and then minus a number. Same number on either side, so these x-intercepts are equidistant away from this x value of the vertex, or the line of symmetry. Okay, just thought I'd point that out. Sorry for no examples, but I'm trying to keep these videos fairly short, so I hope you like that.